Welcome to Unit 6. Unit 6 is all going to work on how do we name a variety of different chemical compounds. So, like I've said before and off and on, in chemistry, things really build from one concept to the next. And so, this really starts to show some of the things we've covered. And moving forward, we're going to be using chemical naming for the rest of the year. And so, this is kind of where things really start to snowball in terms of topics. So it's very important that if you find yourself struggling, you really need to advocate for yourself, speak up, say something, set up an appointment with me so I can work with you on any issues that you might be finding yourself with. So for today's topic, you need to find a way of taking the notes, whether it be a hard copy of it or digital. You're going to need your periodic table, something to write with, and maybe a highlighter for a few things might be useful as well. And so we're going to kind of dive right into naming what's called binary ionic compounds today. And so everything has its own means or ways in which we name. So we've been talking where we kind of left off in Unit 5. One of the topics we covered with the periodic table is deciding, does an element want to gain or lose valence electrons to get to that octet? And so we have what's called an ionic compound. And I know in biology you talk a little bit about bonding. An ionic compound, like the name implies, it's a compound, meaning it's made out of 2 plus elements, and it's ionic, meaning it's made out of ions. So that means you have 2 components to an ionic compound. You have what's a cation, remember those are your positives. Opposites attract in terms of charge. So it's made out of an anion as well with that negative charge. And so that opposite electrostatic attraction is what brings these 2 ions together to then make a compound. So when we look at the structure of the periodic table, the metals being on the left side, nonmetals being on the right, where they are in terms of their valence electrons, metals like to give up their electrons, making cations, nonmetals like to take in electrons, and so that's where we get that positive-negative attraction. So we can have ionic compounds. There's kind of 2 different types of ions. There's what's called a monoatomic ion. So you probably recognize the prefix here, mono, means that it's made out of a single atom. So when we looked at calcium as an ion, that's a monoatomic. When we looked at fluorine as an ion, that's monoatomic. We'll get into polyatomic later on. You probably recognize maybe poly from like polygons. And so poly just means many. So we have some ions that are made out of more than one type of element, and that's something that we are not going to get into today. We're going to work with everything that's monoatomic, or it's made out of one type. So there's rules in which we name the cations versus what we name the anions. So cations, those are, again, the metals because of their configuration. They tend to lose their valence electrons to make that positive charge. And again, those are our cations. And so we have kind of a predictable pattern to what kind of charge they might like to make. So when you look at your periodic table, and you can go ahead and add this to it, we have the alkali metals here, family 1. They like to make a +1 charge because they have 1 ion. It's easier for them to lose 1 electron than to gain 7. So above the family, and something that you can decide, go ahead and write a +1. So something like lithium will always make a +1 charge. When you're in family 2, the alkaline earth metals, you have that S2 configuration. They have 2 valence electrons, so it's easier to lose 2 than to gain 6. They like to make a +2 charge. Remember, this is the D block of the configuration and the F block. Those are metals, but they do some different things because of that D and F block in terms of their valence electrons. So they don't have a predictable charge like these 2 here. And so we'll get into how we name these later on. They have their own branch of naming. The last thing I want you to add right now is, so at family 13, we have this metalloid boron, we have the metal aluminum, and everything else down is also going to be a metal. However, these metals over here start to kind of do some weird things like those in the D block here. So the one thing I want you to mark right now is go ahead and box in aluminum and draw an arrow with a +3 charge. So right now you should have a +1 above family 1, +2 in front of or above family 2, and then a +3, and again indicate that is going with aluminum. So again, when we show a charge, we show it by an exponent or like a superscript after the symbol for that element. So there is a box here on your notes. Go ahead and fill this in. So when we name something that's a cation, in terms of naming them, these are really easy to work with. All you need to include is the name of the element plus the word ion. So to practice here, sodium, if you go ahead and take a moment, sodium is found in family 1. So sodium as an ion is going to make Na with a +1 charge. So if we wanted to name this, this would be called a sodium ion to indicate that it's no longer neutral. Strontium, if you look for strontium, it's an alkaline earth metal, meaning it makes a +2 charge. So we can show that as Sr +2. And kind of the same thing. This is really easy. We just name it a strontium ion. And last one, we have aluminum. Again, that was the one, I know my screen's cut off a little bit here, but that's the one we drew the arrow with. So we have Al +3, and we just call it an aluminum ion. So the moral of the story here is that when you name something the metal, the cation, you don't change anything about its name. So when we name anions, they follow a different rule. So nonmetals, these tend to gain the valence electron. So carbon kind of starts at that tipping point. So carbon has 4 valence electrons. So it kind of has 1 or 2 options to go through. It can gain or lose. Carbon tends to gain electrons to form that octet. So it likes to make a -4. As you move into family 15, it's a -3 because it's at 5 valence electrons. It's easier to gain 3. The oxygen family is at 6 valence electrons, so it's easy to gain 2. And then the halogens here like to gain 1. Again, the noble gases aren't going to form a charge because they have the correct number of valence electrons. Therefore, they don't form ions. The other thing I noted is that these are only for the nonmetals. So notice here I kind of have this lavender purple boxing in the nonmetals. Again, this part or region of the periodic table is blended. We have these metalloids here along that stair-step line, and then down here we have some metals. So you want to go ahead and box these in. The ones that are boxed in are the ones that apply to that rule. So carbon out of 14 is the one that makes the -4, nitrogen and phosphorus -3, oxygen, sulfur, selenium -2, fluorine down to acetine with the -1. So go ahead and take a moment and pause the video if you need to. And I would go ahead and recommend finding a colored pen, pencil, highlighter, something to group that part of the periodic table. So from there, how we name them is different. And the reason why is we need to indicate that we are now working with a compound once we combine this monatomic anion and cation together. When you look at your periodic table, we have 2 options. We can either change the name of the cation or the name of the anion. The reason why chemists chose to change the name of the anion is there are way fewer nonmetals than metals. And so it just makes the system easier by changing just the nonmetal name versus the name of the metal versus nonmetal. So when we go to name them, we use the stem of the name. We add this to the end, a suffix, "ide," and then we add the word ion. So when you look at your periodic table and you find oxygen, when oxygen makes an ion, it's here in family 16. So it likes to form a -2 charge. So we can write O with a -2. So the stem here, and this is going to get definitely easier with time, the stem is ox. The rest of the name is going to go away, and this forms the oxide ion. For nitrogen, when you look at your periodic table, nitrogen's here in family 15, it likes to make a -3 charge. So we have N -3. So NITR is the stem. The ogen, kind of like oxygen, disappears and it becomes the nitride ion. At this point, the only suffix we're adding here is "ide." Phosphorus falls in the same family as nitrogen. So when it forms an ion, it also becomes a -3. Phosph is the stem. Everything else goes away. And it becomes the phosphide ion. So I have a few more practice examples with naming them. And so the halogens are kind of an easy group to work with. If you look at all of the name of the family, or all the elements in that family, they all end in INE. So that's the part you're going to remove. So for example, we have fluorine, bromine, iodine, and chlorine. So the ene is what's going to be removed, and everything to the left of it is the stem. So fluorine becomes fluoride, which when you go to the dentist, you probably recognize that. They give you the fluoride treatments with those trays that they fill up with the foam. If you look at your toothpaste, it probably talks about having fluoride added to it or in it. And different cities, depending on how the water treatment plant cares for water, sometimes fluoride is also added to the public water system. So bromine becomes bromide. Iodine becomes iodide. Chlorine becomes chloride. So that just leaves us with two last examples. So for selenium, the IUM is the suffix, so that makes the selen the stem, so that becomes selenide. And sulfur, the is the suffix, sulf is the stem, so this becomes sulfide. So again, what I've gotten at so far in this video is when we go to name a compound, we're going to start combining our cation with anion, is that we don't do anything with the name of the metal, but when we go to name the non-metal portion of the compound, we have to change the ending. Again, the reason why we do that is to indicate we are now working with a compound versus an element. And then again, we have fewer nonmetals than metals, so it's easier to change the fewer endings on the nonmetals versus metals. So these are the rules for how do we write a chemical formula. So one formula you're very probably familiar with is table salt or sodium chloride. There is a reason why it has a formula NaCl. Water, for example, we know is H2O. There's a whole reason on why that formula is H2O, and these are kind of the steps that we go through. So I'm going to walk you through those and not just read this off to you. So the first thing that you do, and we're going to work in these two examples here where I've already given you the charge, is that would be the first step. Notice that in both these examples, the cation is listed first and the anion is listed second. That's just a normal standard procedure for chemists. You always place the metal first, or the positive charge. The negative charge or nonmetal is always second in the formula. So if you look at your periodic table, potassium makes a +1 charge, calcium makes a +2, phosphorus a -3, oxygen -2. So then the next step of what you do to come up with what is the chemical formula, the goal here is to make a compound that is neutral. We want to get both elements, the metal and the nonmetal, to have a complete octet. And so what you do next to show that is you cross down your charges. So I show these two arrows crossing down. What you do from there is you bring down the charge without the sign. That's going to become what's called a subscript. So what I showed here is I had K. I'm crossing down a -3. The minus gets left behind, and I write that as a subscript 3. So this becomes K3. I write my next symbol, which is P for phosphorus, and I'm bringing down a 1. So in algebra, when you see an X, that's the same thing as saying 1x. So when we have a subscript of 1, we don't indicate it. Just like in algebra, you typically don't write 1x, you write just x. And so what it's telling us is it takes 3 + 1 potassiums to neutralize a -3 phosphorus. So it's a 3-to-1 ratio because of their charges to get everybody to the octet and we are now done. In this next example, we have Ca plus 2, O minus 2. The rule is once you have charges is you cross them down. So Ca is bringing down the new subscript is going to become a minus 2. You leave the sign behind and it becomes a subscript 2. On the O, you cross down a 2 as well. Now, in this situation, we had a 3-to-1 ratio. If there's an instance where you can simplify all subscripts, simplify them. So there's no way to simplify a 3-to-1 ratio and to keep a whole set of numbers. In here, this is a 2-to-2 ratio. I can simplify those. What's both of these numbers divisible by? Well, that's going to be 2. So our new subscripts are 1. So it's really saying Ca1, O1. We don't usually show the 1, so we just say CaO. So what that tells us is that this is a 1-to-1 ratio, that it takes 1 plus 2 cation to neutralize 1 negative 2 anion. Okay, so for the remaining examples, what I've done is I've left off the charge, and that's where you're going to use your periodic table to indicate those charges. So the next one we have is lithium. Lithium, if you look on your periodic table, is a plus 1 cation. So I'm going to go ahead and write that in here. Carbon is a minus 4 anion. Now we're basically at where those two previous problems left off. You do your cross down step. So lithium is going to have a new subscript from the carbon. You leave the charge behind. So it's a 4. Carbon is getting a 1. We leave the positive behind, and because it's a 1, you don't need to write that. If you have the ability to simplify and keep whole numbers, then you're going to. There's nothing that both of these go into that we can keep whole numbers, so we are done. In my example here, we have Al and N. Al is a plus 3 charge. Nitrogen is a minus 3 charge. So we're going to show our crossing down. The subscript that's being brought down to the aluminum is now 3 without the charge. The subscript that I'm bringing down to the nitrogen is the 3 without the charge. Looking at my combination here, I have a 3-to-3 ratio. They're both divisible by 3, so I can simplify these out. So it becomes Al1N1. I don't need to write the ones, so what it's saying is this is a 1-to-1 ratio. It takes 1 aluminum giving up 3 electrons, 1 nitrogen gaining the 3 to get both of these to an octet. Here we have Na and Cl. Na on the periodic table is an alkali metal. It likes to make a plus 1 charge. Chlorine is a halogen. It likes to make a minus 1 charge. So I'm crossing these down, and because in both instances it's a 1 that's being crossed down, I don't need to write the 1, and I do not need to include the charge. So to show it's a 1-to-1 ratio, we just write NaCl. So this is why it's so crucial to make sure that you're writing your uppercase versus lowercase. Make sure that you're always capitalizing the first letter. If there is a second letter, make sure that you're lowercasing it. So as we start writing these compounds, we can understand what is found in the formula. Last example here is aluminum and sulfur. Aluminum, right here, is a plus 3 charge. Sulfur is in the same family as oxygen. It makes a minus 2 charge. Go through my cross down method. Aluminum is going to have a new subscript of 2. Sulfur is going to have a subscript of 3, again leaving the charge symbols behind. Now, there is nothing that both of these subscripts they're both divisible by, in which I can keep whole numbers. So this one will not go through simplification, and you'll keep the subscripts on both. So this has kind of, again, been a step-by-step process. So in the big picture is where do we go from, or why do we need these formulas, is as a chemist, when I go to make solutions in that, oftentimes they're labeled with the full name. And to make a solution to the correct concentration, for example, I need to know its formula to do some math with it. So what I would do here is I have aluminum fluoride. I can see aluminum is first, so I know that's my cation. I can see fluoride. That suffix change is telling me it's a compound, and I know that this stem tells me it's fluorine. So the first thing we do to get to that formula, like we just did in the table, is you're going to write your symbol. So we have aluminum. The cation always goes first. Aluminum is a +3 charge. Like I said, fluoride is indicating fluorine. So I know that F is its symbol and -1 is its charge. Now we are right where we just left off, practicing with the table. So the one step I left out was the full name. We are at the part where we do our cross down step, and this becomes AL with a 1, so I don't need to write the 1, F subscript 3. Again, there's nothing I can do here to simplify subscripts and keep whole numbers, so I am done. So this tells me the formula for aluminum fluoride is AlF3. Last example with this style then is magnesium sulfide. So magnesium I know is Mg, and I know that magnesium is a +2 charge. Sulfide, I know that I'm working with a compound because that "ide" ending, and that my anion is sulfur, so I know my symbol is S, and it's a -2 charge because of its 6 valence electrons. Crossing my subscripts down through that cross down method, it's going to become Mg2S2. Both of my subscripts here are divisible by 2, so it's going to become Mgs, indicating it's a 1-to-1 ratio. It takes 1 magnesium to neutralize the octet or complete the octet for a sulfur, and vice versa. So the last part for today's lesson is if you want to go ahead and take a moment. In this column here, I want you to look up the charges. So for example, magnesium you would find as a +2, and iodine is a -1. And then I want you to come up with the formula by crossing down charges. So we have Mg, I2. If you want to go ahead and take a moment and fill in these remaining 3, this would be a good time now to check if you're doing these correctly or not. So when you continue with this, aluminum, you should have identified as a +3, phosphorus is a -3, calcium's a +2, nitrogen's a -3, and then strontium is a +2, and carbon is a -4. When you did your cross down steps, you should have discovered that you get Al3P3, which simplifies out to ALP, aluminum with a phosphorus. So here we have calcium +2 with the nitrogen -3. So on calcium, we bring down a subscript of 3. Nitrogen, you bring down a 2. You have no numbers in which you can divide by to keep whole subscripts, so you're going to leave that one alone for simplification. And this last one here with strontium and carbon, you do the cross down method. We get SR4C2. Hopefully this one you can recognize that it can be simplified. So you have to understand what do both have in common in terms of terms that will divide in. They are both divisible by 2. So I'm just showing my step here so you can understand where I get my final answer. So it becomes SR2C. And so that is the correct final formula for this particular compound. So the last thing that's new in this chart then is going to the original name. So up above in this table, we went from the name to a formula. Here we have the formula. Now we're going to name it. And so that's what this last column is for. So the part that's easy is naming the cation. That's always listed first, and that's stated up here. The cation is named before the anion. So you would just name it as Mg is magnesium. Al is aluminum. Ca is calcium. And Sr is strontium. So the part that is important is the anion is what's named second, and because it's in a formula, this is where we do our "ide" ending. So we know that our anion here is iodine. To indicate that it's in a compound, we change it from iodine to iodide. So if you see MgI2, we have magnesium iodide. Aluminum, our nonmetal, is phosphorus, so that becomes phosphide. And that's where the front side on your notes when we named the nonmetals, that might be kind of a useful little crutch, so to speak, as we work on naming these. Once you start naming these and get more practice, it kind of becomes like riding a bike. You just kind of pick them up. So the last two here, we have nitrogen. Nitrogen changes to nitride, always that "ide" ending. When I start teaching this, I sometimes get students say nitrate and nitrite. Those are what's called a polyatomic. You maybe have tested for that in water, maybe back in middle school potentially. So again, right now, everything has an "ide" ending. So the last one we have is carbon. So the suffix there that we're going to get rid of is the "on." So we have carb, and then you add "ide." So that becomes a carbide. So if any of you have a parent that works with different power tools and things like that, I know you can buy like different drill bits and stuff like that that are carbide based. So if you want to ask them if they've ever worked with it, that is something you could do. So anyways, that is topic 6.1. If you have any questions, want extra practice besides the posted assignment, or want me to check something over on the assignment, please reach out to me with any questions.